I'm good.
So let's start again with Lorenzo.
Yep. Okay, so now we start to build on what we've done so far, and there I killed everything but the summary of what we get to. We have an old problem with the new dress, and we're going to try to use this dress to solve the problem. So the problem we can, the way we're going to phrase the problem is this is just a sum up with a new name that I didn't use, and we're going to discuss it a little bit. So we are giving a probability space, which is a product of an input and what we think as an input and an output and a distribution. We have n pairs of samples, identical independently distributed. We assume that you have a space H of function from X to R of candidate solution, which is a Hilbert space with continuous evaluation functionals, and the name of this space is reproducing kernel Hilbert space. We'll discuss a bit more in a second. Then we have two operators, a discrete operator, which evaluates the function at the training set points, that because of the properties of this space can be written just this way, as the inner product of F with this special representer, and its continuous version that now take F and evaluate it any point in the distribution, in the marginal distribution. These are our ingredients. Given these ingredients, our goal is to solve this linear system, provided we have knowledge only of an approximation of this operator and an approximation of this. More precisely, this operator S rho and F rho are not known, and what we have are these discrete operator that I just redefined, and where there is the dependence on the input data, and then yn, which is the vector of the outputs. All right? So this is the basic setting. The two ingredients, the probabilistic one and the analytical one, and the problem. The Calvo observation that we made, we can define the minimal norm solution according to this linear system that I here write in a slightly more compact form than the one I wrote before by introducing the normal equation that corresponds to least squares. If you remember, the Nonparametric solution was among all the least square solution, find the one with minimal norm. Well, these are the set of least square solution. This is the normal equation of least squares. So this is just a compact way of writing it. This might replace F rho as the target of our problem in case of F rho is not realizable by the space of function we've considered. And the last point we made before is that the nature of this data is somewhat atypical and unusual because this operator and this operator don't live in the same space. They have the same domain but different ranges. So we need to find a way to compare them. And the way we're going to do it is exactly using the idea of, rather than comparing this problem with this empirical counterpart, compare their normal equation. And this suggests that these two quantities could be reasonable if our goal is to estimate the noise, or if you want, the perturbation. Again, the term noise here is somewhat inexact because typically noise is just some kind of additive multiplicative deformation. Here is really some kind of discretization. You know, the sampling is contained in here. Okay? So far so good? These are our ingredients. Okay? What do we want to do next? Well, let me spend I just want to spend 5 minutes about these spaces a bit more so that we have a couple more tangible examples. And we discuss a bit the important nature of this assumption, okay? Both from a practical and a theoretical point of view. And then move on and discuss regularization. So remember that an RKHS is what I defined before. It's a Hilbert space with continuous evaluation functionals. These spaces have 15 different definitions. Well, 15 no, but there's at least 4. They're all equivalent to each other, and this is by far the most abstract one. And we used it just because it does the only thing we wanted, which is to give us this kind of representation that gives us linearity. It's not the practical one, and it's not the one that has any practical value. The thing that is typically used is the fact that if you consider this function, if you define, so let me do it this way, given a space, there is a unique function defined this way. And this is what they call the reproducing kernel of the space. It's called reproducing kernel because if you do f times kx, by definition you get f of x. You reproduce the function at the point. By construction, you see here that this function is symmetric and positive definite. Symmetric means what you all know. Positive definite means that if you build the matrix, any matrix of m points with entry k, xi, kxj, it's easy to check that because of the way this function is defined, this matrix is positive semi-definite. The eigenvalues are either positive or 0, but they cannot be negative. And this is a nice exercise to prove. You can just prove it in the case where you just have inner product of any two vectors. It really relies on the fact that this function looks like this. Okay? Why is this an interesting fact? Because there is a one-to-one correspondence. So here we said, if we start from these two abstract assumptions, we end up with this special function. You can also go the other way around. You can also start from one such functions and build a space with this property. And we don't want to do it here because we don't want to discuss too much about this, but I just want to give you some example of kernels, okay, that would make sense to use. Again, what we did here is start from abstract assumption and end up with a special function. There is a theorem, the Mura-Ronzagin theorem, that tells that you can go the other way around. You can start from this positive definite symmetric function and build the function with this property. This is a standard result. So in your head, you can think that in practice, typically the way you do is that you start with this. Okay? Let me make some examples. The simplest example of kernel is the inner product of two functions. In this case, I'm assuming x is Rd. Okay? And all my examples are going to be just for the case x equal Rd. The linear product is the simplest case, and in this case, the associated RHS is just the space of linear functions. So f of x is just going to be sum of wj xj for some wj from 1 to d. Another thing you can do is that you could consider this to be any finite expansion on some dictionary of function phi j. So phi j here are any function from x to r. And I just write this kernel this way. Phi jx prime. And then the function here are just going to be the linear combinations of function on this dictionary. This is just another example. Any dictionary, okay, just any finite collection is going to give you a kernel. These are all examples of finite dimensional kernels. The last example you can consider, we can consider 5 billion example. The last example I want to show you is the case where you consider K to be a Gaussian. Okay? It's easy to check that this is symmetric. Checking that it's positive definite requires a bit more gymnastic, and a way to do it is to go and just look at the Fourier transform. If you look at the Fourier transform, you can essentially use a standard resultant functionality, the so-called Bochner theorem, that ensures that that's positive definite, but it's not checking that these two are positive definite is an exercise. Checking that this is positive definite, it's a bit more than an exercise. You have to rely on a fundamental result. If you go check what are the functions in the space, these are functions that are not band limited, but they have an exponential decay in Fourier. Okay? Again, the initial discussion when we introduced this space, I told you L2 is not okay, Cx is not okay. But I announced that, for example, if you look band limited functions, so function that the limited content in frequency, that's okay. You can actually relax this assumption. You can assume that you have some decay. And the Gaussian kernel corresponds to an exponential decay. You can further relax it and consider, for example, a polynomial decay. And you will get other families of kernels. Okay? Why I'm telling you this story? Well, first of all, because I want to show you that there are some concrete objects behind this space, these kernels, that they're super crucial because you see that they do induce assumption on the space. I'm basically restricting the, as we said from the beginning, but here we see even more clearly, we restrict the search for a solution to a finite set of functions. And then there is a big question that I would like to raise, comment, and kill, which is how do you choose a kernel? Okay? Well, it's a fundamental question. How do you choose a kernel? Which one is a good kernel? And this is basically what's missing from the theory right now, and it's really what a lot of people are working on, try to find heuristic to find good kernels. Now, the way you should think about anything I said is not that something that takes the raw data and thus produce magically a fantastic function set. The way I'm thinking about this is that you get the raw data and somebody either learn or tweak enough the data to get you in a format where then you're left to exploit some form of nonlinearity on top. Okay? So that's typically the way you think about it. This is like a last step. Okay? If you look at any, or say 95% of any practical problem, is not just one step of inference. That's a legend, okay? That you take the data, you put them in one single box, and you get the solution. You typically put them in a box and do a few steps, okay? Now you can do them separately, or you can try to do them jointly. But the steps are always many. The single step procedure are never used in practice. There's always some, say, pre-processing, some extraction step, and then there is some step like this, and maybe there is also something afterward. Okay? So this is just to warn you the way you should think about this. You should not think this as something that lives alone in a world where there's nothing else before and after. There is a lot of stuff before. There is a lot of stuff afterward. My attempt is just to clarify a bit how this stuff is useful. And I'm going to take the fact that this guy is given just as a recognition of the fact that there is more stuff going on. Okay? That's not what this series of lectures is about. This series of lectures is about is different computational way to exploit this kind of framework once somebody got you to the point that you can use a kernel. Okay? And if I manage to get time, I'm going to try to show you the kind of result that you can get using the fastest possible algorithm in this. If, for example, compare them to, say, neural networks that are in principle schemes that are divided in several steps and try to couple all these steps at once. Okay, so where are we? We have this. Okay, and we have some specification of some more words about the space. The idea is that H is going to be given, the data are given, and we don't know the distribution. We want to try to solve this problem. I told you a minute ago that now we can start to steal, and I mentioned at least one algorithm. Which one? Tikhonov regularization. What is Tikhonov regularization? In our notation is now the following. Consider the minimum of f in H of our problem on the data, okay? Which is S n f minus yn square plus lambda f square. This is the norm in Rn, okay? These are just vectors. This is the norm in the reproducing kernel Hilbert space. Fair enough. Let's play with it a bit. Well, before even we start playing with it, okay, this is Tikhonov. Okay, what kind of question we want to ask about this guy? Well, you can ask two questions. The first question is, how do you realize it numerically? And the second question is, can we show that this actually provide a good solution to this? And how much can we steal from inverse problem and how much more we need to do? Okay? The answer to the last question is basically going to be we can steal 80% from inverse problem, and then we have to steal 20% from covariance estimation and law of large numbers. The emphasis is going to be really much more on the linear algebra part, if you want, or functional analytic part. From a numerical point of view, which is what we're going to comment first, there is an easy case and there is another easy case, but they cost one line. How do you solve this thing? Well, what is the easy case? Assume that you are in either this case or this case. Then effectively you can recognize H to be essentially a finite dimensional case of some dimension P, either the dimension of the data or the dimension of the feature space induced by a dictionary. Then you have that functions are really just vectors, and that these operators are really just matrices. Okay? That's all you have. And then you can go in, let's just derive this guy. What do you get? So again, same as before. Set derivative equal to 0. Let me skip it because we did it before. Then all you have to do is to solve this linear system, and then you get your function f and lambda. It depends on the data, and it depends on lambda, and is the minimizer of that. In the case where I'm in finite, so this is the case where H has dimension strictly smaller than some P. Okay, the space is finite dimensional. Then this is just a P by P matrix. I have to build it, and then I just have to invert it. Everything is finite dimensional. And we can ask, for example, what is the time and space cost of solving that? How much is it? You know? We have to invert it, which is P by P. If you really go and try to some kind of find a direct solver, this is going to be roughly P cube. Even before you can try to solve it, you have to build it. So you have this matrix, which is P by N, and this one, which is N by P, and multiply them. And this is going to cost you a P squared N. So this is your cost in time. Okay? How about space? Well, essentially you have to store NP. Okay? All right? Now, these are pretty rough estimates, okay? So I'm using a direct solver. You can say, why don't you use some kind of iterative solvers? Why don't you try to, instead of pre-computed things, recompute things on the fly? We're going to discuss that. This is just a benchmark, okay? This is not trying to be fancy, just to be pedagogic and simple. And this is arguably the default complexity, at least in the worst case. Okay, the other question I want to ask is, what if H can be actually infinite dimensional? Okay, what if, yes?
Here, P is supposed to be larger or smaller than N?
For now, it doesn't matter. I mean, you can also do the other way around. So I guess this one is the one where P is supposed to be smaller than N. So what Gabriele is saying is, and we're going to use it in a minute. So let's say that in this case, P, we suppose, is smaller than N, I guess. Okay? So let's, for the sake of it, we're going to exactly see what's happening the other way around. So let's say it this way. So let's consider the case where we do finite dimensional and P is smaller than N. Okay? Then you can ask, if you want, two questions. What if P is larger than N? And actually, what if P is infinite? Okay? So I just jumped ahead a bit, but the intermediate step is also interesting, okay? Then what you can show is essentially the following lemma, which is the basic of basically the few things that we know to do and we call non-parametric statistics, at least one of the bases. If you look at the solution, you can always write it like this. where the matrix Kn is the so-called kernel matrix. So we suppose that we have the kernel in our hand. We build a matrix, which is the matrix of all the product among all points. And then what we do is that we add lambda n on the diagonal, and then we invert it, and then we apply this to the vector yn. And this is a vector of size n. This is a matrix of size n by n. This is a vector of size n. And then you get this linear expansion. Okay? How do you prove this? Well, instead of how you prove it, let's first see why you get this. Okay? The reason why you get this is so before how you get this, let's just check what are the computational costs of this operation. Okay, let's believe it for a minute. Then what do you have to do? Well, you have to build this matrix. How much is it going to cost you? Well, you have n points. You have to compare n points against n points through the kernel. So this is going to give you a time complexity, which is n squared, times some constant, which is the cost of evaluating the kernel among any 2 points. And then what do you have to do? Well, from the time point of view, you just have to invert this matrix, which again, following the same line of reasoning as before, this will be n cubed. Agreed? And space? Well, you basically have to store the kernel matrix. What if my kernel is not infinite dimensional, but is, for example, one of these two kernels? Well, for any of these two kernels, you see the definition is still here. You can tell me how much is CK. How much is CK for those kernels? Well, they're just inner products over P or D dimensions. So this is just, in the special case where the space is finite dimensional, CK becomes P or D. And you basically see what Gabriel was noticing before. If P is smaller than n, yeah, go with this. If P is not infinite but is larger than n, don't do this. Do something like this. Because you see that in the complexity, if you call this P, the role of P and n somewhat interchanged. And so you just have a linear dependence on P, which is very big, and you allow yourself, in this case, a pretty bad dependence on n, which is cubic. Then somewhat we swap.
It's Woodbury formula, right? Linear algebra, it's Woodbury.
Where it's coming, yeah. It's a bit less than that, actually. It's simpler than that. It's SVD. Okay? So this is what it does for you. It swaps the role of the two dimensions. And if one of the two is infinite, you just rely on the fact that you can compute the kernel. Okay, what is infinite here? Well, the dimension of this feature space. For example, for the Gaussian kernel, I can compute the kernel. It's going to basically be dependent on D, but I don't know even if it's an infinite dimensional space per se. Okay. So this thing here, you know, that you see in a minute that it's very easy to prove. It just takes 2 lines. It's basically the basic of nonparametric, a bunch of nonparametric statistics. And this is the, so what, if you want, frequentist way of deriving it. You can basically rederive the same thing from a probabilistic point of view, a Bayesian point of view, and call this the maximum posteriori estimate of a Gaussian process, whose covariance function will be given exactly by the kernel. And these are basically the 2 main points of view of how you build global non-parametric estimator for regression. Okay. How do you prove this? Well, there are essentially 2 steps. Okay. But the main one is this linear identity, which is basically what Gabriele was referring to. I tell you what I want to do. I want to take this matrix here, okay, and pull it in front of the parentheses. I want to take this S star n and put it here. To do it, I have to swap these 2 guys. So the first step of the story is just And basically, this is almost the end of the story. Why is this true? Sorry, this is a mistake. Okay, so it's S star S. Okay, I pull this guy in front, and then you can convince yourself that something like this has to go on just from a pure dimensionality point of view. You see that these two guys have to swap. Consider the case where S is just, if you want to convince yourself, just consider the case where S is the n pi p matrix. Okay, the easy way to prove this is just by checking that it's true by computing the SVD of this. So consider this to be a matrix, compute its SVD, plug it in there, and check that this equality is true. It's a completely trivial exercise in linear algebra. There's nothing in it. In the notes, I think in the end, if I remember correctly, I put a bunch of small exercises that there are places where in the text I skip steps like these. And it suggested that you do it because I present all the proofs that you can do in a reasonable, very short amount of time. This is one such steps. This is almost the case if you remember what are this operator and this operator. The operator as star is just, if you apply it to a vector A, is just 1 over n, I from 1 to n, kxi, ai. So you take you remember it was the story of the harmonic expansion. That's exactly it, okay? It has that phase. You take some numbers and you combine the kernel elements. If you look at S star n, this is 1 over n kn, this kn here. Because essentially you do this, you first take A, just evaluating the function, and then you apply this non-harmonic extension, and that's exactly what you get. Okay. Also, this one is a small exercise, and by no means this is supposed to give you the whole step of the proof. These are the main steps of the proof. To show this, you start from this, you swap the order, and then you realize that you get a sum that is essentially what gives you this, and then this operator inside is essentially this. Then there is like half a line of linear algebra to finish. The reason why I'm showing you this is not to give you the whole story, but just to show you how simple it is to do it. You have to advocate nothing but basic linear algebra, and you can just get the result. So the place where we're at right now is that assuming that we do have a kernel, and we just want to go the Tikhonov regularization way, we can do numerical implementation in the finite dimensional case or in the infinite dimensional case. And why do we call this stuff non-parametric? Because even if we allow ourselves to work in principle in an infinite dimensional space, we obtain function representation that are given just by n coefficients. So they're in some sense parametric, but the number of parameters is not fixed a priori, but it changes. As you get more data, you have to estimate more coefficients. So in this sense, it's automatically adaptive to the amount of data you have. And in this sense, we would call it a this is like a working definition of a non-parametric technique, as opposed to a parametric technique where the number of parameters is fixed by you a priori, and then you have to change it in some sense by hand. Here it changes automatically. Okay? All right, so the good news here is that this method is simple. It reduces, his story is basically that in inverse problems, a bunch of people thought about this essentially around the 60s. Tikhonov in the context more of integral equation. In statistics, this is what is called, in the special case where you consider this to be just the matrix induced by the linear kernel, it's called ridge regression. And again, it came out basically in the 60s. The good news is that it basically just jump into linear algebra. So you get linear systems. And so that's nice because basically it breaches statistics with a huge amount of literature on numerics. The bad news to some extent is that all these complexities are, especially the non-parametric ones, are really not affordable when you start to go in large data sets. Okay? If you have a data set of 1 million points, you need to store a matrix which is 1 million by 1 million. Okay? And you know, on your laptop, you can probably go up to, say, 20,000 by 20,000. On a big workstation, on a big machine, you can probably go up to 100,000. But there are no computers existing in the world for which you can really store this. So you have to start to think about how to do things differently. And the challenge here would be, can we do something better than this? Okay, and how far can we push it? One reason why people like this, you know, and use it somewhere in the pipeline is because you can say a lot of nice things from a statistical point of view. We commented on the numerical aspects, but we can ask about statistical properties of this. In particular, in which sense that problem solved this. You remember, in the case of inverse problem, the idea was to show that if you choose lambda depending on the noise, then you can show that certain nice thing happen. Can we show something like this here? And that's what we want to do next. Yep. Kn is the matrix with entry kxi, xj. So k is the kernel, and then you compare any two pairs of points, and you get a symmetric matrix that is kn. Okay? So up to here, so I stole from inverse problem, I wrote it, and I did nothing. Then I did a linear identity, and I got a bit more. I got, if you want, non-parametric. So this is the first ingredient where I combine a bit statistical, no, not statistical, but say, I put to work inverse problem to give me something that I can reinterpret from an estimation point of view. Questions so far? Okay, so in order to do the, what's going to happen essentially that we want to prove something that says, okay, this is the estimator given by that procedure. This is this Moore-Penrose solution for the learning setting, is the best solution in my space with minimal norm. Tell me how far they are. Maybe for some specific choice of the parameter. Okay? Specify also how I have to choose the parameter. Now there are a couple of questions here. Okay, which is the good norm? What is the good metric to measure distance between this? In inverse problem, the standard thing is to consider the norm in the solution space. So again, you have an operator that goes from one space to another space. The standard thing is to consider the norm in the solution space, what they call H here. Because of the connection between the L2 norm and the risk, in learning theory, it's actually more natural to look at the norm in the other space. So say if this is the norm in H, it would turn out that it's actually more interesting for learning to look at this norm. Because if you remember that little the little equality I wrote before, this gives you a connection between looking at the risk, the error on future data, and a norm that you can manipulate as a norm. So next, I'm just going to consider this because it's simpler. And because once you get the analysis right for this, you have to add a few more technicalities and you get something for that norm. Okay? So just keep in mind is that once you have to measure how different are these functions, you have to ask what is the right metric. In inverse problem, this is the standard one. In learning, this is the natural one because it has an interpretation in terms of risk. But it turns out that the analysis of the two are very much related. And just for pedagogical reason, this is basically just a little bit simpler to do. You just have to take out one extra complication. So we're going to look at this. In order to get some kind of bounds on this, we're going to have to make some assumptions, okay? And the assumptions we're going to make are some boundedness assumption, just because they make our life easy. So I'm going to assume that kxx prime is smaller than 1 almost surely for all the x in my distribution. This is clearly true, for example, if you use a Gaussian kernel. In general, it might not be true, for example, even for the linear kernel case. This can be relaxed. I just want to keep this, and I put a 1 because it's simple, okay? And you'll see where it enters. You see exactly where it enters, and when you go and comment on it. I'm also going to make the assumption that the yi, that my output, are also all smaller than 1, almost surely. If you want, this is a bounded regression kind of setting. And again, I just want to do this because that's not what I care about here. And we'll see exactly where this assumption enters. We assume that this guy exists. And this will be enough to prove some kind of convergence, but it will not be enough to prove convergence rates. For convergence rates, we're basically going to assume that some condition of this form exists. Okay? So there exists a G in H such that this is true. What does this mean? Okay, so you take this operator, you apply to this function, and so remember that these operators are nice, okay? This operator S star rho S rho is an operator from, so I want to explain this a little bit and to try to give you an idea of why it is an assumption. It is an operation from H to H, and under this assumption, it can be shown to be a symmetric operator, positive definite, and compact. What do we care about? Just that you can consider its eigenfunction. They provide the basis for this space. This means that just by assuming that this function exists, I would have that I can write that f dagger is equal to f dagger rho. Say, let me call ui sigma I the eigenfunction and eigenvalues of this operator. Then I would have that I can just write ui. It's a basis. I just write the function on that basis. Then I can take the norm, and by Parseval identity, I just have that this is equal to f rho dagger ui square, which basically tells that the sequence of these numbers has to be a little L2 sequence. All right? For now, I made no assumption besides the fact that this function is in the space. What is the effect of making an assumption like this? It is in some sense a smoothness assumption. What does it say? You can basically reformulate this, checking that it says something more. It says that not only these series have to converge, but it has to converge once I divide by the square of the eigenvalues. Okay? So the sequence converge. Now I divide by the sequence of, the square of the eigenvalues. The square eigenvalues, you have to remember, are a sequence of positive numbers that converge to 0. So now I'm basically dividing this for something that goes to 0, and I require this to be still finite. Okay? So what does it mean? That not only I ask my function to have a decaying sequence, but I put condition of how fast it decays. Think a special case. If you assume, for example, to consider for something like an exponential kernel, then you can write all this stuff in closed form. And what you get is these ui are essentially the sine and cosine. And you get the sigma I are some kind of polynomial decay sequence. Then you can really view this as a Fourier or smoothness-like assumption. This is just my function is in L2. This is my function is not only is in L2, but is in a subspace of L2 where it has a certain decay of the Fourier coefficients. These just become, again, these become the Fourier components. These are the Fourier coefficients, and this is the decay assumption of the Fourier coefficients. Yes?
Characterize those kind of source conditions for other than non-smoothness classes. When you're not in smoothness classes, that's great. Is it easy to find such kind of solution?
So the question is, okay, you write this down and you give me an analogy. Okay, you're basically saying, for Fourier, I know what it is a decay of the Fourier coefficients. For other eigenfunction, I can still see without having to give example what it means. You basically say I write coefficients and they have to decay faster than just like this. They have to somewhat counterbalance this. Now he's asking, can you characterize them? What does it mean characterize them? It will basically mean, can you have an equivalent definition to this that somewhat give me another insight? Not really, not really. There are many examples you can take, okay? The complication of this is that it's really a generalization of the assumption of smoothness, which now makes it a bit more interesting, because the assumption of smoothness is typically settled in a space where you have to work, say, in RD, function is in RD, with a measure that has to be either a uniform measure or at least a measure with the density which is somewhat bounded from above and below. And even that case becomes a mess because you have some kind of multiplication operators appearing due to the measure. This stuff is implicit, but it holds much more generally. For example, now you can play the following game. You can say, let me take a specific kernel, something like a Gaussian kernel, and now support it on a manifold. Okay? And now you can try to characterize this kind of condition in terms of manifolds. And what happens is that rather than the Fourier basis, you will get something more similar to the eigenfunction of a Laplacian operator, and then you have some kind of intrinsic analysis on the manifold. So we don't want to go there, but it is just to say this is kind of an entry point of different way to characterize smoothness. Sometimes you recover standard settings. Other cases you just have a much broader assumption. The nice thing, if you want, is that the function space here, the nice and bad thing is that this is really assumption on the conditional distribution. There is basically no assumption besides this on the marginal distribution. It can be literally whatever. Okay? I'm just assuming the kernel to be bound. Once I look at the marginal distribution through the kernel, it got to be bounded. But other than that, I'm making no assumption. So in some sense, this is a condition on the conditional distribution, an assumption on the conditional distribution that depend on the marginal. And so I can allow myself freedom in choosing the marginal in different ways. And this is somewhat different from the classical way to think about smoothness classes in a completely distribution independent way. Of course, if I assume that that marginal distribution to be uniform, then I go back in standard setting.
I'm just in trouble with notation. So you have this compact operator S star S.
Yeah.
And you suppose that you have spectral decomposition, and you denote Ui the eigenvectors and sigma I squared the eigenvalues.
Sigma squared just become from the fact that I'm considering, so yeah, you should do this.
Yeah, sure,
just
okay.
For the norm.
But so you assume that G is in H, so I think you want that
I'm writing here, there is a norm here.
Okay,
I just write smaller than infinity.
Don't get it.
I'm just invert this, okay? So this.
If you start from the right, you know that the coefficients of G are just summing up.
Let me write it like this. This relationship is equal to assuming this.
Okay, so you start from this point. Okay.
So instead of writing it like this, I write it like this, and then you can get it this way.
Yeah, sure.
Where you have to divide. And then you really see that what you're doing is...
So this is a G coefficient, in some sense. The last line.
Again, it's really just this.
Okay.
So this norm, which I wrote here,
yeah, sure.
Okay, if you want, is equal to this, and this is finite.
Yeah, thank you.
Okay. Yeah. So his question was just, okay, you wrote it this way, then you wrote it this way. Can you just do the one step to go? Yes. Take this, and just this means, if this is true, then it means that you can, on this function, you can really, on this function, you can invert it. Invert it and write this norm, and then this norm. If you do it, you get this, because here you're applying this operator to the -1. The square just becomes from the square norm, and that's what you get. And then you really see that you're basically restricting yourself to function that have some kind of decay. Okay, So in the mean, while we're having the discussion, we basically stated a couple of things, which are this assumption is standard and inverse problems and is called source condition. It oftentimes has a physical interpretation. In the context of learning, it does not have a physical interpretation. It's a prior assumption. You can view it in special cases. It recovers standard smoothness conditions, such as Sobolev condition or more general condition. It generalizes them to the situation where you have more general setting. You consider, for example, cases where your data are supported on a manifold, but more generally you just have this intrinsic definition, which is completely depending on the marginal distribution. So in some sense, this is nice in general. All right, end of the parenthesis on the assumption. This is going to be our assumption. What do we do with it? We use them to try to study this quantity. So let me see if I can just write down the theorem, and then we try to prove it. The idea is that we want to prove something like this. That if you choose lambda equal to n to the minus 1/3, okay, order, there are constant here. Then, with high probability, or if you want in expectation to make it simple, you have that f, let me call this lambda n, is up to constant smaller than n to the minus 1/3. Okay? We want to try to see, at least start some proof of this. But let's check 1 second, what does he say? He says roughly that, the noise is something that behaves like 1 over n or 1 over n to the 3rd. Okay? When you were thinking about noise going to 0, here you think about n going to infinity. Before, we said, well, when we have no noise, we should not regularize, so lambda should go to 0. Here, we're basically saying, if we have a lot of data, we should not regularize much. So when n increases, lambda should decrease. Here, we're doing a bit more than what we did before, because we not only provide the result that says when n goes to infinity. Before, we said when delta goes to 0, the error goes to 0. Here, I'm telling you how fast. And that's the reason why we dwell with this assumption a little bit. Is this a good result or a bad result? It's actually a good result. I think, sorry, just one thing. I think there is a square here. I'm not sure if there is a square or not, because in the notes I might screwed up, but now we prove it, so we check whether it is a square or not. The point I was trying to make is just that this result is actually good. It's actually optimal in a minimax sense. So if you allow yourself to choose any possible procedure to estimate this function, under this assumption, you cannot do better than this. Okay? This third comes essentially from the fact that we're allowing ourselves to be infinite dimensional. If you make more assumption, you can get something better than this. If, for example, you say, well, I know something about the decay of the eigenvalue. Maybe I even know that my function space is finite dimensional. Then you can get better than this. And for example, you can make this 3 into a 1. Okay? But in the non-parametric setting, you don't get that. Okay? So this is gonna be our point in future algorithm. We're gonna try to keep this and try to get something with better computation, but the same kind of statistical result. What we want to do now is to at least start to see how you prove this result. And as I told you, it's going to be primarily a bunch of linear algebra. The starting point is essentially that we want to try to we're going to relate the empirical solution to the ideal solution by an intermediate step, doing a classical decomposition, which is not quite a bias variance decomposition, but almost. And we're going to do it for any fixed lambda and get the bound. Then we're going to try to optimize the bound and get the rate. So to do this, we have to introduce a function. I call it f lambda, which is the argmin, is kind of the, if you want, the so-called population version of the algorithm. It's the continuous version of the algorithm. So I allow myself to have perfect knowledge of the distribution, but I still regularize So I regularize, but here I put the true operator, the true datum, and the exact norm. It's kind of something in between what I can do in practice and what I would like to do in theory. It's similar to what I do in practice, and it's in the limit when lambda goes to 0, it seems similar to what I would like to do in theory. If you take the gradient to this, set it equal to 0, and you see what you get is the same thing we had before. Okay? It's just the same thing. You just take the gradient, set it equal to 0, see what you get. There are a bunch of ways to prove that these two things are close. One way relies essentially on working directly with the variational problem, okay? And try to use techniques for empirical process theory. What we're going to do is that we're actually going to use directly the explicit form of the solution and do linear algebra on it before later on we use probabilistic tools. So rather than working with this expression, we are going to work directly with this expression. And this is going to make it more about the linear algebra than anything else. Okay, so what do? We add and subtract this function. And we get two terms. I call the first S lambda and the second A lambda. The difference between the first two terms is I do run the same algorithm for real or hallucinating and assuming that I could have access to infinite data. The second case is I run the algorithm with infinite data, always in the hallucination state, with lambda equal to 0 and with lambda not equal to 0, roughly speaking. The first term is statistical in nature, whereas the second term is deterministic and it's just a geometric term, an approximation term. The first term I will be able to bound essentially only using these two. The last term you'll see that I really need something more. That's where the no free lunch comes. You really have to make some more assumptions if you want to make it go to 0. The way we proceed is going to completely decouple the probabilistic side of the story and the analytic part of the story. Let's look at A lambda. What we're going to do is that we're just going to write things down and look at them. So we get that guy. Let's skip one step and I tell you what I did. So here I should write f rho, but because this is a solution of the normal equation, I know that this, well, let me do it. I should write S star f rho, okay? But because it's, if you look up there somewhere, you know that this is a solution of the normal equation. So it holds that S star f dagger is equal to S star rho f rho. So I can replace S star rho f rho with this, okay? And then you see that I have f rho and f here, and I also have it there. Remember that f rho is the true solution, f dagger rho is when I project it. So let me write it. What do you get is S star rho plus lambda I minus 1. I plug this in here. I get S star rho S star minus identity. I should write here F dagger rho, but you see I have my assumption there. So instead of this, I can actually write here S star rho S rho times my G. I just plug in the assumption number 3. Okay? I'm going a bit fast here because I'm doing nothing. What do you have to do now? Estimate the norm of this operator. It's a bounded operator. Okay? It's always the same quantity. You just have to, I want to just to take the sup norm of this operator and compute what it is. If you want, you can do a middle step where you simplify this a little bit. So if you write here, if you take this times the inverse and you write it there, you can simplify this a little bit and you get so you basically call this B and write here B minus 1. So you get this thing that multiply S star plus lambda. You can simplify one step and you get an extra lambda. Okay, I'm going a bit quick because it's not so important. The main point is that now you want to estimate the norm of this. So lambda is just equal to the norm of this. But now all you have to do is to just estimate the maximum for sigma between 0 and 1 of lambda sigma divided sigma plus lambda. Okay? It's just the definition of the characterization of the operator norm. That's all you have to do. And basically, roughly speaking, this is going to give you something order 1, and this is going to be order lambda, up to constants. The constant is going to basically depend on this norm of G. Again, let's go over it again, but it's pretty simple. You just write down the solution of this continuous version of the algorithm. You subtract the ideal solution, and then you just do linear algebra. You use because you want to factorize f diagram, you use the fact that this is the solution of the normal equation, and you get here. Then you really need to assume this. And you see why it matters. Suppose that here, instead of this, I put 0. Okay? I put alpha here, and I put it equal to 0. What happens? This term disappears. But then I get this sigma goes away, and I don't get any rate anymore. I cannot give an explicit bounds. You really just see that you get close to the, you can prove that this thing goes to 0, but you cannot prove any explicit bounds. So this is exactly where we use that assumption. And if you want, you can generalize. If you generalize, and instead of putting here 1, you put a generic alpha, instead of lambda, you will get some lambda to the alpha. Okay? It's easy to generalize. But we don't want to do it. Okay? So all we are basically checking is that for lambda going small, we can really prove the convergence of this function to this, at least if we know something about the function we're looking for. And this is, I didn't skip any, the only step of the proof I skip is the one where you study, when you study this one-dimensional function. Okay, that's it. So the bias term you can characterize very easily. Is it clear? It's also late, but does it make some sense? So what I hope you see here is that the proof is nothing. You just use, again, don't be fooled by the fact that we talk about operators. Think of these as just matrices. And these are just linear algebra. We never use anything particular, okay? If this is matrices, it's all the same. And you see where the prior assumption that we discussed for a bit enters, is to estimate the bias term. Is it okay, or is it a mistake? It could be a mistake at 5:01. 5:30, very long. Okay, yep. I'm sticking to the norm in H. I use the norm in H. Okay, this is always the norm in H. In fact, I just take the function and I never have to put them in L2. Okay. Again, I do this just because if you do norm in L2, you just get an extra annoying operator that you have to deal with, and it's a technicality, but it's annoying. It actually costs some sweat, but there is no conceptual change. So this is all going to be norm of H. Just to go also back to a normal thing, if you're considering, say, regression in linear regression, it means that I'm not looking at prediction, but at parameter estimation. If your functions are linear, so they're Wx, I'm looking at the W's, the convergence of the W's. Just basically, I'm allowing my W to be infinite dimensional. Okay? That's basically what I'm doing now. Okay, the next step, which is going to cost a bit more pain, is actually to consider S lambda. Are there any questions about this while I make it disappear? Monte. Okay. Also in this case, it's going to be mostly some linear algebra, and then at some point we'll have to deal with a couple of random variables. And by the way, if you're familiar with the analysis of ridge regression in the linear case, this is up to a change of notation the same thing. We're just we're doing exactly the same thing. Okay, if you call S X, is the same. Okay, I'm just going over it again because then I'm going to use it, and I just want to show you that it holds in a more general situation. So let's look at S lambda. S lambda is equal to Fn lambda minus F lambda, which means S star n Sn plus lambda I to the minus 1 S star n Yn S rho. There's going to be a lot of writing here. So that, by the way, that proof is taken out of a book of inverse problem, okay? I just have to call, I could not, I didn't do anything new. You could say, let's call A S rho and let's call G F rho, and you get it for free. So in that case, there was nothing new. In this case, what we're going to do, we're going to use similar ideas, but we have to change it slightly. The novelty is going to be in the analysis of the random variables. So it's inspired, but slightly changed. So what do we do here? Well, we have these two terms, and we're going to, in some sense, you see, the thing is that with respect to, say, for example, other standard analysis of ridge regression, here we have that this part is afflicted by a perturbation, but also this part. So you have to, in some sense, try to decouple the effect of these operators and this part. I would like you, to find something linear that depends on these two terms. And so that's what we're going to do next. And the way we're going to do it is through some kind of additive bounds, because it's simple. So what do? We take these two things and we write something somewhat in between. So the first term we're going to write takes this part and add it and subtract it. So I get S star n Sn plus lambda I to the minus 1, and then I get this because I already had it. And then I get this because I subtracted. Okay? So I had this term times this, and I subtract it. Now I want to add it. So I have S star n Sn plus lambda I to the minus 1. I would have this. It also appears here, so I factorize it out. So I'm skipping very small steps, but if you get lost, let me know, and I can just write them down explicitly. Okay? So I have terms 1 minus terms 2. Then I add and subtract a term which is made of this part times this. And the first time I factorize this empirical operator, and I get exactly what I wanted, the difference between somewhat this kind of error in the diatom of the right-hand side. Okay? Here, almost, I have to sweat a little more. What do you have to do? Yeah. All in H. Everything I do is in H.
Everything, yeah.
So that the whole trick here, you know, at the high level, I have Rn, I have L2. I don't know how to compare them. So I add this extra space H, and I always use this extension operator to put me in this common space. Yeah. That's the trick. Okay? I extend things to a common space, which is distribution independent, and then in a metric, which is distribution independent, I start the distribution dependent operator. That's all. Okay? Do you see where this is coming, more or less? I'm skipping one step just because I'm going to die otherwise. Okay, so what do you do with this? What do you say in English? Minimum common denominator. A minus 1 minus B minus 1. If these were numbers, it's particularly easy. If these are operator, you still do the same. You basically say A minus 1, B minus 1. I'm just writing it because if you've never seen it, I'm going to just skip it, but it's trivial. So you just write the identity like this, okay? And then you get A, B minus identity B minus 1. And then you write the identity as A minus, sorry, A minus, well, I made a mistake. You write identity as A minus 1A. So you basically do minimum common denominator for, so you write these as A minus 1A, and then you get B minus A, B minus 1. Okay? So let me just work on this second term for a minute. So I'm going to get A minus 1 plus lambda I minus 1, and then I get B minus 1 and then I get B minus A. Okay? So I have to take the inverse of this, and subtract. So clearly the term lambda I goes away. So let's see, that's B. So I get S star rho, S rho minus, okay? Which is exactly what I wanted. I do get the two pieces I wanted. Okay, now what do we do now? We first take norms and we kill everything that we can kill. To do this, we basically have to understand what is the norm of an operator like this. You have again to just do the calculation I wrote above. You remember that the characterization of the operator norm can be done because of spectral theorem just in terms of real valued function. And basically what you have is that terms like this are going to be order 1 over lambda. Okay? Again, this is computing the maximum of a real valued function. We're not going to do it. This term, we have to think a second about it, just because I tell you what, I'm shooting, well, no, let's say, I'm shooting for this 1 over lambda. This would spoil it. This term turns out to count order 1, because again, remember that S star rho F rho, I can replace with the, using the normal equation. So instead of this term, I can actually write S star rho, S rho, F dagger rho. This is my assumption on the fact that the normal equation admits a solution. And then I don't have to study this operator, but actually this. So I have an extra term here. So this is not 1 divided sigma plus lambda, is sigma divided sigma plus lambda. So this is actually order 1 plus a norm, which is a number and it is finite. Okay? This is the second term. What about the first term? Well, the first term is this term, which is 1 over lambda, and then this stuff. Let me put everything together. Let me call this term delta 1, and this term delta 2. And then we can write, putting everything together, a first estimate, which for now is completely analytic, which tells me that the difference between what I do in practice and what I could do if I have infinite data is 1 over lambda. Delta 1 plus delta 2, or delta 1 and delta 2 are two quantities that now we have to estimate. Okay? Again, the step of the proofs are just add and subtract something, factorize, common denominator, or is called in English, and then just operator norm, okay, of this term and then of this other term. And we use it whenever we can, this normal equation. What did we use up to now of those assumptions? Well, essentially, the first one is a bit hidden what we use. The kxx smaller than 1 is what allows to say that this, you see that there I wrote the sigma is between 0 and 1. The eigenvalues are because 0 and 1. They're because between 0 and 1 because I assume the kernel to be bounded. So we used it there, okay? But we don't use for now the y boundedness and the assumption on the source condition, the prior assumption. Okay, we're basically done. What we need to do is estimating this guy and this guy. And the proof is very similar, and I'm just going to show you one. The basic idea is to write this down and look at them. If you write this down, you can really see that this is just kx, outer product kx. Okay? You remember it was just the covariance. Okay, so if you want the linear case, it's sum of x transpose. Okay? That's all it is. Kxi. If you look at this is the same thing with an integral. Okay? Again, these symbols here just stand for, if you do kx, this means just kx is the rank 1 projection. Okay? Which in the linear case is just xx transpose. Okay? There's nothing strange here. Okay, these are the two guys. Okay? If you look at S star n yn, this is equal to 1 over n, I from 1 to n, kxi yi. And this is going to be equal to d rho x y, kx f rho x. Okay? Well, now what you have is that you have something that looks like an empirical mean and its expectation. The only thing is that these are not just numbers. These are functions in a Hilbert space, and these are operators. Now, what I'm going to use here is actually the simplest result you have, which is basically the one that extends Hoeffding inequality from numbers to vectors, or if you want, functions. So Hoeffding inequality in its basic form says that if I have a sum of bounded vectors, zi, and I want to bound with high probability their norm, I get something that up to constant is order 1 over square root of n. The constant is going to be then the bound on the random variable. Probably Stefano better who's the one that really did it, but you know, the extension, at least the extension I know, is due to Pinelis and Jurinsky, and it's basically saying if you put here a norm, if instead of saying, I don't have numbers, I have vectors. Actually, I don't even have vectors. I have function in a Hilbert space, or vector in a Hilbert space. So instead of absolute value, you put a norm. Essentially, the same result holds. It's more complicated to prove, but it holds. Okay? So at this point, this vector can be easily shown to be bounded. This is bounded. You just plug it in. And so you can prove that delta 1 is up to constant smaller than 1 over square root of n with high probability. Here, you have to decide what you want to do. The simplest way is to use a Frobenius norm. So you see them not as a bounded operator alone, but you see them as Hilbert-Schmidt operators, Frobenius operator, and then you can just easily use the same result. Okay? I'm glossing over it because here you can do a bunch of things. The basic idea is you can just call these zi and use results where you work in the Frobenius norm, and then it's elementary, or you use some more sophisticated concentration equality like non-commutative burst, and you work there right in an operator norm. The thing I'm just going to try to communicate here is that you don't have to do, you take an inequality and you plug it in, and you just check that things are bounded, and then it's for free. And you get that these two terms are both order 1 over square root of n. So we end up with this bound. Okay? And those inequality hold with high probability. You can integrate them out and get expectation result if you like. And here you see that these two terms don't really depend on the assumption on the regression function. We are not using anything. The only thing we use is the boundness here to bound this and to bound this. That's all we need. And you see why I'm saying, allow me to just do those brutal assumptions, because you're going to see if you're smarter than me, you can just make them weaker. Because all you need to do is to basically say, okay, instead of working with bounded random variable, let's control the moments of this random variable, put the assumption you like, and you can just go up there and replace them. Okay? But I saved myself 5 minutes to write stuff and pretend it was interesting. It was not. I mean, it's something you can do on top. Okay? Well, but we're done. We proved the theorem, basically, which disappeared, but it's there. So let's actually... So just remember this 1 over lambda square root of n, and so I go back up if I manage. Is it this one? Okay, so this result tells me that the norm of a lambda is smaller than lambda. The result that I conveniently just completely covered for mu said this is order lambda square root of n. Okay? So now I just do the triangle inequality. I took the square because I want to simplify things. And what you get is that fn lambda plus f rho dagger square is less or equal up to constant than 1 over lambda square. Maybe I made a mistake. Let me check. No, it's okay. So sorry, so it's a 1/4 here. I made the assumption a little stronger. So you get 1 over lambda square n plus lambda square. Okay? In my notes, I made the assumption slightly weaker, and I get a slightly worse assumption here. So this gives you a this gives you exactly what you wanted. It gives you lambda. So if you now take this, you just optimize over lambda. You get you lambda over n to the 1/4. You plug it back in, and you get the result. No? So Daisy, you just make them equal. You get lambda squared. You get lambda to the 4th, 1 over n. You invert. You get this. No, sorry, you're right. You see, looking at Stefani is useful. You plug this in, and you get n to the 1/4. Okay? So you plug this back here, and you just get square root. Okay. Yeah. I had a mismatch in my notes. So he was frowning because, so you get in my notes I put a 2 here and a 1 here, so I got a slightly different result. So you get a 2 here and a 2 here. You get n to the 1/4. You just plug it back in. So here I just make these two terms equal, which is okay because they're just polynomial rather than taking the minimum. And then here you get the n to the 1/4 become 1 over square root of n. Okay? In my notes, I put here 1/2, and that's where the 1/3 come about. That was still true that it's optimal under a weaker assumption. Here I'm making a slightly stronger assumption, and I get the square root of n. Okay? If you put here alpha, you get the whole family of rates, essentially with minor modification of the proof. All right. almost done. Actually done. We should just do some blah blah to finish. And, all right, so we sweat to get this inverse problem stuff. We stole an algorithm from inverse problem. We start to look at the theory. We found out that half of the theory was for free. We just had to recognize the meaning of objects. They were not source condition. They were smoothness condition in a general sense. Then we go to the stability part, if you want, the one I hid here, the one where you see the effect of noise and sampling. There you take the philosophy of the proof, but you change it a bit. You proceed in a purely analytic way, basically doing linear algebra. You add and subtract operators, take some norm of operators. And then in the end of the day, you really have to do the one step which is different from inverse problem, where you have to take care of the noise. You get to the point where you define, now let me do this again because I lied. You define some noise, which really plays, you know, morally plays the role of the noise. It's not quite noise in this classical sense. It mixes up sampling and the noise in a classical sense. But you see it in some sense mathematically it plays the same role. Once you've done that, you stop and you say, okay, let's estimate the noise. And that's what you do here. Once you've done that, you put everything together and you get the result. And you get this basic statistical result that tells you, okay, how to choose lambda in order to get the optimal rates. Okay? Let's make a couple of comments. As I told you, instead of that -1 in my source condition, I could put an alpha. And which one is the right one? I don't know. Do you know? Nobody knows. It's just a prior assumption. We're inventing it to get some rates. So ideally, we're going to get all rates. If you do that, the annoying bit is that your rates are going to depend on alpha, how much smoothness, how much speed you have, but also the choice of lambda is going to depend on that. And then it becomes important how you can choose it in practice, because alpha you don't know. And that's why it becomes important to have data-driven procedure. And if you want, I don't know how many years of model selection, provide you ways to do that. The game is, I know that there is an alpha, but I don't know it. Can I still choose lambda so that I'm going to get the best possible rates? Let's keep principle, complexity regularization, cross-validation, hold out cross-validation is probably the simplest way to prove that this can be done. And so we're not going to discuss how to choose lambda in a good way, because we don't have anything to contribute there. We're going to actually make one observation, which is the implication of having to choose lambda for real in practice from a computational point of view. The idea that you can solve that problem only once for one fixed lambda is a lie in practice. The cost of computation is not the one I wrote up there. That's a lie. You always have to solve that many times for different lambdas, and then you have to pick one using some other criterion. So in the cost you see up there, you have to multiply for a number of lambdas that you're going to try. So you're going to discretize your models, and then you have to try a bunch. And this is an overhead, okay? At least a number of logarithmic number of lambda needs to be tried, and this is going to, you know, if n is a million, it's going to be somewhat of a big overhead you have to pay. What we're going to try to do, next is try to provide algorithm, as I said, they're going to have exactly this kind of same statistical properties, but we're going to try to work on their computations. The good thing is that what we're going to do tomorrow, what we're going to start with is basically just doing optimization for a while, and then just saying, oh, I just want to relook at this algorithm from a different point of view, not as optimization algorithm, but as learning algorithm. Instead of doing this kind of relaxation approach Statistical regularization is based on, we're just going to go straight to do optimization. We're going to skip the first step. Instead of relax, we're just going to go and optimize something. And then we're going to discover that optimization itself, in a sense, is doing regularization. And this gives some kind of new perspective on the way you estimate things and some links between, again, statistics and optimization. I think that's all I have to say. If you have any questions.
Thank you.
He's got the microphone. He's the boss.
I'm not sure I understood how the third assumption there, S rho star, S rho, that there exists such a G. is a smoothness assumption?
So depend what you, he said smoothness, so I said yes. But we have to look at what we mean by smoothness, okay? So what do you mean by smoothness? Typically it means that you either do the Fourier transform and you have a decay, okay? Well, I guess the normal way to say smoothness is that you take derivatives, then you can integrate them, okay? Fair? Let's ask Gabriel first, because if he says no, then we cannot proceed. What is a good definition of smoothness? Perhaps the simplest one is it's smooth if you can take derivatives, say. Okay? Then one way to go beyond this is to say, okay, instead of derivatives which are discrete, let's do the Fourier transform and use that characterization. Then being able to take derivatives means that you can actually have some kind of decay in the spectrum. If it's discrete, it means that you have some coefficients that goes down. If you take a basis which is not Fourier but something else, in some sense you have also kind of smoothness. You take a basis and you have some kind of decay on that basis. Now, depending who you ask, he actually might call it sparsity. What do we call sparsity? You take a basis, it's finite, and you say some coefficients are 0. But then you want to be fancy because you like functional analysis, and you say, well, they're not 0, they decay. Then it means that you have to order them, and you have some decay. So then you can decide how you want to call it. Is a smoothness assumption on the eigenfunction, or is also sparsity, a weak sparsity assumption on the eigenfunction of that operator? Make sense? Here.
Yes. So up to now, what do you gain from the Bayesian analysis, the Gaussian process point of view?
What I gain?
No, what do we gain? What do we have that we would not have with the Gaussian process point of view until what you present today?
Well, so the question is what you get out here you wouldn't get from Gaussian processes. So I would say the Gaussian processes, at least the majority of the work I know, the emphasis is more, so this is just, in Gaussian process, basically, you start from a Gaussian distribution on the functions, you write everything in terms of likelihood and probability distribution and a posteriori distribution, and then you say maximize or take moments. The emphasis is typically to go beyond the first moment, which is what I'm doing here. I'm just getting the first moment, but say I don't have any do estimation of uncertainty in a probabilistic sense. So for now, from that perspective, I lost something. From what I did, I would say in the majority of the Gaussian process literature, the emphasis is not on the frequentist result that shows a consistent estimation, say, of the maximum posterior and so on. But indeed, there are. So from that point of view, there is still some overlap. And so from that point of view here, there are some differences, but they're not major. I would say they're minor. Tomorrow, I'm going to present things that somewhat do the same, but I cannot see as maximum a posteriori. So tomorrow, I think it will be a much more interesting question to see how these things are doing some kind of, what is the probabilistic interpretation? Because there I can always just put an exponential and say, oh, it's a probability distribution. Tomorrow, I'm just going to do something different, and I don't know if there is any way to have a probabilistic interpretation. In a good way and in a bad way. The good way is that I do get something more. The bad way is that I want to get back and get uncertainty. Here is for free, because I can just go back to Gaussian processes. There I won't be able to do it. So the short answer to your question is not much. I'm basically treating everything from an analytical point of view rather than working the probabilities. And I call RKHS instead of Cameron-Martin spaces, which is what I learned last week.
Okay, is there any questions? So thanks, Lorenzo, again. Thank you.